Welcome back to our series on statistical mechanics. Today we will be discussing and defining one of the important sectors in the statistical mechanics, what we call as the partition function. So, partition function we will be defining in canonical ensembles. In the last episodes, we were in the process of developing statistical mechanics in the classical regime. Originally, we started with the general framework of statistical mechanics. Then, in the last few episodes, we decided to specifically target the classical treatment in the development of statistical mechanics. There, we introduced the concept of ensembles. We use the framework of phase space, which is the QP space, as otherwise we call it, to explore such a ensemble system. And in the last episode, we introduced the concept of density function. As part of our discussion, we evolved an equation, or we derived an equation to represent the evolution of density function through the Liouville's theorem. For the next few episodes, our attempt will be to explore how these ensembles work in this new framework, the new framework which is offered by the classical treatment, the new framework which is offered by the phase space, and the new framework which is based on the broader concepts of the ensembles. You know that mainly we have the microcanonical ensemble, canonical ensemble, and the grand canonical ensembles. So, these are the three main kinds of ensembles available. During the discussion on the ensembles, I already put across the point that the microcanonical ensemble is a purely theoretical proposition, because the imagination that we could keep the energy constant will be really a theoretical proposition, because practically it may be taught is almost impossible. So, we have two kinds of ensembles which are really connected to the real world experiments, the canonical ensemble and the grand canonical ensemble. So, let us start discussing on the canonical ensemble. We have already defined what is a canonical ensemble means by, so we are not doing it again over here, but here our attempt is to evaluate the entropy and other thermodynamical quantities in the canonical ensemble. So, our effort for the next 1 or 2 episodes will be to evaluate or evolve an expression for the entropy of canonical ensembles. Similar to entropy, once you have the entropy, you can similarly calculate based on the entropy, you can calculate the other thermodynamical quantities also, like the free energies or so and so forth, or the enthalpy, whatever it is. So, first and foremost, our attempt should be to calculate the entropy. In order to reach the process of entropy, we need to go through a quantity called the partition function, which we will try to define in this episode. So, as we know, in the canonical ensemble, we can keep the system at a constant temperature. So, how do we do that? I think I have discussed it already. The easiest way that you can keep a system at a constant temperature is to keep it in a heat reservoir, right. Heat reservoir. So, there the only limitation for such a system is that the system should have an infinite heat capacity. So, we assume that the system or the example which we will be considering is having an infinite heat capacity. So, here we know that we need to keep the NVT constant, so that the macro state will have the NVT constant. So, let us try to explore such a system. So, what we do is that let us take a ensemble or a box in which a box of ensemble, right. So, it's I define it by A0, which is represented by, which is having an energy E0, and of course, it is having NVT constant. So, the energy is allowed to vary, but for the entire ensemble the energy is a constant, or energy is preserved or conserved, which we define as the E0, right. Let us imagine a region within this box, which we call as A, and it is, its energy is say ER, and it is obviously kept at a constant temperature T. So, this region within this ensemble box is defined, is we call by the A, and what was our attempt? Our aim is to keep it at constant temperature. So, we already decided that we should keep it at this system within a heat reservoir, which the heat reservoir I call it as say A dash, which is represented by ER dash T. Obviously, there is the N and the V, but we are not doing anything which can disturb the number of particles or the volume of the system. So, therefore, I am not writing it each and everywhere. So, we have the A, which is immersed in a heat reservoir A dash. Now, our assumption is that at thermal equilibrium both the systems will have a common temperature. That means, the reservoir and the system which we assume will have a constant temperature T. So, therefore, I am putting the temperature T over there. And talking about the energies, we have three energies ER, ER dash and E0, and the limiting conditions are that ER will lie between 0 and E0, okay. And similarly, I can put the other limiting condition ER dash is also lying between 0 and E0, and what else? And obviously, we know that ER plus ER dash is equal to E0. Most importantly, this is a constant, because we are not allowing any external system to affect our ensemble box. Okay. So, this is how we define the system. Now, let us think about the kind of probabilities which are there. Okay. So, we define a probability PR . So, PR is the probability for the system A to be in the system, to be in the energy value ER. So, PR is the probability for the system A to be in the energy level ER. So, I can write A of ER T. So, this is the probability, right, and this probability, otherwise I can assume that it is proportional to the number of microstates which are there in this region. So, PR is directly proportional to omega ER. I am always safe to assume that, and we have made already this discussion, right. And similarly the PR dash, what is that? PR dash is the probability for the for my the reservoir to be in the energy ER dash. Right. So, those are the two probabilities, but for me it is more convenient or more credible to define this probability PR as directly proportional to omega dash ER dash. And I will tell you in a moment why. PR is directly proportional to omega dash ER dash. Okay. Why? Because this is a very small, although I have put a for the representation purpose, I have put a bigger area, assigned a bigger area in this box, but actually this area is very much negligible. The area A is very much negligible in connection with the full area of the or the full volume of this ensemble box. So, therefore, as far as the number of microstates or the count of microstates is concerned, the reservoir is having a large number of microstates compared to my assumed region A. Okay. So, it is more credible for me to write like this. A real world example for you people to understand is that, let us imagine that there are two persons, person A and the person B. Okay. Person A likes blue balls and the person B likes red balls. So, in this box which we are imagining, there are say 99 blue balls and there is one red ball. So, the person B will always pick only the red ball and the person A will try to pick the blue ball. Okay. So, if that is the case, now if A is going to pick the ball with eyes closed, so first A goes to pick the ball with the eyes closed. So, the person B who is waiting to pick the red ball will always wish that the A will pick the red ball, the blue ball, because the moment if in case the person A picks the red ball, the chance of person B getting a red ball gets reduced, right. So, the person B will always wish to have the person A getting a blue ball whenever he goes for picking the ball. So, the probability of picking a blue ball by A is actually proportional to the chance of picking a red ball by the person B. As the chance of person A getting blue ball increases, the person B getting a red ball also increases. But the blue ball is a bigger number, therefore, it is more error free to quote in terms of the probability for the person A. So, therefore, similarly here I can write PR is directly proportional to omega dash ER dash, and you know that ER dash I can write in terms of as ER dash is equal to E0 minus ER. So, if I want to expand it or equivalent to omega dash E0 minus ER. So, there is no mistake in me doing something like that, right. So, therefore, let's continue doing our derivation of the partition function. So, what we decided was that we will pick the omega dash ER dash, right. Now, omega dash ER dash, again I would like to make a modification, right. So, what I'm going to do is that I am going to see how can I expand this this function in terms of ER or the energy, that is what I am going to do, but this will be a fast varying function. So, instead of this function, what I am going to do is that I am going to take the logarithm of omega dash ER dash and I will try to expand it. Always remember that I have put an additional logarithm term over here, which means that whenever I get into the formula, I will have to always discount for this logarithm in my later part of the derivation. So, logarithm omega dash ER dash is a slow varying function and therefore, I am going to use this function. So, let us expand ln of omega dash ER dash is equal to, what I will do is that I will use the famous Taylor series for my expansion. So, you can write it by yourself, ln of omega dash ER dash. So, when I use the Taylor series, let us imagine that, so what is Taylor series? According to Taylor series, Fx is equal to Fa plus f dash a by 1 factorial into x minus a plus f double dash a divided by 2 factorial into x minus a the whole squared plus etc. So, this is the Taylor series. So, we are going to expand this ln omega dash ER dash based on this the famous Taylor series. Here, here for this expansion, we will take x is equal to ER dash and what else I need? I need a. A is equal to E0, which means that we are expanding it about E0, right? Right. So, expanding, I will get ln omega dash ER dash is equal to ln of omega dash E0, right, plus dou ln omega by dou E dash is equal to E0 ER dash minus E0 plus higher order terms. So, this is what we will be expanding it, right. This is how we will be expanding it. So, if we look into this expansion, we know that this term ln omega dash E0, which is this is going to be a constant, right. So, there is a constant. If we define a quantity beta, if I call beta is equal to dou ln omega dash by dou E dash, so then I can define ln omega dash ER dash is equal to a constant. So, this ER dash minus E0, I can now I write it in terms of ER. So then I can write a constant minus beta ER, right. So this is how I will define the that function. So therefore now earlier I have told that PR dash is equal to omega dash E0 minus E0 minus ER, right. Yeah, this is where PR is equal to PR dash is equal to omega dash E0 minus ER. This is how I started with, but now instead of PR I am having ln function. Therefore I can readjust on that, and I can write it as PR is directly proportional to exponential minus beta ER, and this function, the exponential minus beta ER, is what we call as the Boltzmann factor. And based on this function I can write down this PR now in terms of a constant C as PR is equal to C exponential minus beta ER, or sum over PR is equal to sum over C exponential minus beta ER. So what is sum over PR? Which will be 1, and therefore so sum over PR is equal to 1, and based on that I can now write C is equal to 1 by sum over exponential minus beta ER, right. And then the whole PR, if I substitute the C over here, I can write PR is equal to exponential minus beta ER divided by sum over exponential minus beta ER. This is what we call as the canonical distribution. So this I can write PR in terms as PR is equal to 1 by Q exponential minus beta ER, where Q is what we call as the partition function. So this is how we define the partition function. So what is the relevance of partition function? How does it matter in an ensemble, especially in a canonical ensemble, and using the partition function, how can we evaluate the entropy of a canonical ensemble? All those aspects we will discuss in the next episode. Thank you.